So today we're going to finish up the last little bits of our lecture on the basics of making sound with SuperCollider, primarily focusing on a pair of classes named Synth and SynthDef. We'll talk about a few miscellaneous methods that, just to tidy a few things up, and then some helpful graphical server tools. And then we'll move on to our next unit of lecture, which is some creative sampling techniques, and with the general goal of just giving you some tools and techniques with which you can make interesting sound relatively easily. So what I have here is a line of code that boots the server, so we're going to boot ourselves up here. And then I have a UGen function, which I have copied and then changed a little bit from last week. So we have right now one argument, which is a gate used to sustain this envelope. The envelope has 4 level points with these durations between them, these curve values, and 2, which corresponds to this value right here, is the release node, which means as long as the gate is set to a value of 1, the envelope will hold at this value, and when gate is set to 0, the envelope continues to its end, where it meets its done action, which causes the synth to free itself. The sound source in this SynthDef is a sine oscillator, which has a randomly chosen frequency, a reduced amplitude. It's been made into a 2-channel signal by using the duplication shortcut, and here we just apply the envelope to the signal. So we create the UGen function. Doesn't play because we're not telling it to play, we're just defining the function. And then down here we're going to actually play the function and store the resulting process in the interpreter variable x. And in the post window, when I do this, you'll see that what actually gets returned and stored in x is a synth. And so it plays because the gate is 1 and is remaining at 1, but because gate is an argument, we can set it to a different value. So by setting it to 0, this tells the envelope, okay, that's enough, on you go. And it fades out and it disappears. So this method of using a UGen function, and giving it some name, in this case tilde fn, and then playing the function is one way of making sound, and it's kind of the casual, quick and dirty way of making sound. It's basically a shortcut for a more robust process, which involves creating and adding a SynthDef to the audio server, and then explicitly creating a new instance of synth ourselves. And doing it this way, as we have on our screen here, is really just a shortcut for doing that. So what we're going to do is take this UGen function and these 2 lines of performance code, if you can call it that, and we're going to convert this into a SynthDef and a synth. So to convert a UGen function to a SynthDef, let me back up a few seconds. A SynthDef, what is it? A SynthDef is a class that represents a signal processing or signal generating algorithm. So it's a collection of unit generators that all work together to do something specific in terms of sound. And we're doing a shortcut for that here. So to convert it to a SynthDef, we will just give ourselves some space down here. And I'm going to create a new SynthDef. And there's basically 3 steps to converting a unit generator function to a SynthDef. Number 1, the SynthDef needs a name. And conceptually, this is the exact same thing as naming our function, except we don't do things like this. We don't really ever set the value returned of a new SynthDef to a variable. That's because the first argument of a SynthDef is its name. And this is a symbol. I think it can be a string as well, but I usually do symbols. So we'll call this tone. So we've given our SynthDef a name. And the second thing it needs is this argument called UGen graph func, which is basically a function containing the unit generators that you want to use to define this SynthDef. So for the most part, we can just grab our function from up here and copy it and paste it right into the SynthDef. We need to make a few changes, but this is sufficient for now. So step 1, we've given it a name. Step 2, we need to explicitly designate an output signal if we do in fact want this SynthDef to output a signal. And when we do function.play, we take advantage of an internal mechanism that says, okay, there's no explicit output here. I'm just going to assume we're supposed to output the last line. And it does that. But SynthDefs don't do that. They need us to say, you are the output signal, out you go. And we do that with an instance of out.ar. It's a unit generator which takes a destination or a bus and a signal, and it sends the signal to that bus. So what's a bus exactly in this context? Well, we will dive into the details of buses and routing and signal flow later. But for now, all you really need to know is that bus 0 corresponds to your left speaker, bus 1 corresponds to your right speaker. That is a very simple way of putting it, but it's going to take you very far, even if you don't really look under the hood and understand exactly what's going on. And you'll also remember from our brief discussion about multi-channel signals that if you send a multi-channel signal to a single bus, SuperCollider will automatically assign the discrete channels to adjacently numbered buses. So in other words, if we send a stereo signal, or any two-channel signal, which is what we have here, remember we're dealing with a stereo signal, so if we send it to bus 0, it's going to end up being written to buses 0 and 1, which is exactly what we want. We have a two-channel signal, and we want to hear that in the left and the right speaker. So you should basically never do stuff like this. I mean, it looks tempting to sort of, we've got a two-channel signal, let's write it to buses 0 and 1. This is actually wrong, because what ends up happening here is the stereo signal gets written to buses 0 and 1 and 1 and 2, because this is how multi-channel expansion works, basically. It's going to expand this out into two outs, which is each outputting a stereo signal to a different bus. And we end up getting some signal overlap on bus 1, because both the left and right signal end up reading. So this is all wrong. We're not going to do this. The bus of an out should pretty much always be a single number. And the behavior of arrays kind of takes care of the rest. So that is step 2 of 3. We designate a specific output. And step 3, very, very easy to remember, but also very, very easy to forget. We have to add the SynthDef. So we put .add at the end of everything. And this actually encapsulates a whole bunch of under-the-hood messaging that happens between the language and the server, and the language says, okay, bubbity-bubbity-boo, here I go, here you go, and the server receives the SynthDef, and then it's accessible on the server. If we don't put add and run this, we'll try to make a synth and it just will not work, and there will be no error messages or anything like that. It's very frustrating, and I've definitely once or twice spent 45 minutes trying to figure out why sound wasn't working, only to find that I had forgotten to add my SynthDef. So it's very, very important to remember. Okay, and then we evaluate our SynthDef, and we see a SynthDef. If there's something wrong in your SynthDef, like a syntax error, it'll get reported, and you'll have to kind of figure out if you left a semicolon off of one line or you forgot a comma, something like that. So we have our SynthDef, and now we can create a synth by saying x equals synth.new. Synth needs a couple of things. For now, we're just going to focus on the first two things. The first one is the name of the SynthDef that we want to use. And right now we only have one, and it's called tone. Now, sometimes, in a lot of cases, you might have like 10 or 15 SynthDefs, all with different names. In fact, they have to have different names, because if you make a SynthDef with the same name, it's going to overwrite the previous one. It's a sort of one-to-one relationship here. They have to have unique names. So you need to tell the synth, use this SynthDef. And then we need an array of arguments to initialize the synth, basically. And if we don't provide anything, it's going to use the defaults here. But for now, let's just, even though it's redundant, we're going to say gate 1. And if we had more arguments, we would say comma, freak this, amp that, whatever, right? All sorts of things. And there is a syntax alternative here, which I am starting to gravitate towards. This is just a different way of expressing the same thing. You can do the symbol with the backslash and the comma, or you can put a colon immediately after the argument name, and and that's fine as well. So you might see me go back and forth, but I'm starting to like this one a little bit better because it's one less character each time. Okay, and so then we play this, and there we go. We've made a synth. Note that we don't have to say .play anymore. This, by virtue of the fact that it exists, a synth is already active and playing. It is alive and it starts doing its thing based on the recipe provided in the corresponding SynthDef. And then we can say x.set gate 0, just like we did over here, because now we're just talking to a synth. That's pretty much it. The other thing you might want to do when you're making a SynthDef is think, okay, are there any other parameters I might want to be able to change and specify? Because right now, the frequency is always just going to be some random value between 200 and 1,000. We can't specify we can't provide a specific value if we wanted to. We can't change this range. We'd have to actually go back to the SynthDef and edit it, which is something we probably should do. So we're just going to put a frequency argument here. We'll just say, I don't know, 400. And we'll also make an amplitude argument here. Actually, let's get rid of this. And down here, we'll say, let's multiply the signal by some amplitude parameter before we actually send it out. Like that. And it's always a good idea to provide an argument for the bus, I think. Even if you're always going to be sending it to bus 0, it doesn't hurt to have an argument, because in sort of intermediate and advanced contexts, you might be sending signals to other buses if you have some complicated signal flow. So we'll make an argument for this as well. Okay, so pretty much the same thing, except now we can specify other arguments. Here's 300, 500. Right. We can make the amplitude a little bit louder. Right. Pretty basic stuff. One thing you want to watch out for, obviously, is that if you have a sustaining synth that relies on some sort of gate message to terminate it, and you sort of start making a chord, you know, let's turn this down actually. Yeah, we'll just start making some. Now if you run x.set gate 0, it's only going to affect the most recently created synth, because we've got this dynamic environment where we can sort of evaluate code on the fly, and we've made a synth and overwritten the variable x each time. So the other three are alive, and here they are. This is the node tree, which you can open with show node tree. And we don't really have language side access to these anymore. They were stored in X, but X is referring to a synth which has just been freed. So, I mean, command period, I guess, is the best option here. So you want to, if you have multiple synths that are going to exist simultaneously, and you want to be able to talk to them independently, they have to have different names. Right? They have to have their own unique names, basically. There is an alternative syntax for specifying arguments, which this is what you see in all the help files and a lot of, you know, books and examples and things like that. You see this arg statement at the top, and I'm pretty sure I've also mentioned the pipe syntax like this. This is totally fine as well, same thing. But one thing that's a little bit annoying about this approach is that, you know, the arguments appear twice, at least twice. So if you change the name, you have to change it twice. And the arguments don't pop out with a special color or anything like that, so it's kind of hard to track them down sometimes. So as an alternative, you can use a syntax shortcut which involves making the argument a symbol and then putting a rate that you want it to run. By default, arguments will run at the control rate, and that's a usually perfectly fine default, and then give them a value. And so here we have amp out, and there was gate, that's the other one. And this is a kind of a little bit nicer, I think, just because now we can see the arguments at a glance a little bit more easily. We can see their default values, and we've eliminated the need for an argument line. So again, just another alternative, which I think is worth learning. So this all still works. Make sense? Yeah, and it's not a very interesting sound, but just gotta get these fundamentals out of the way so everybody's comfortable with this sort of thing. Okay, quick note. Let's go back to randomness for a second. Now, I had xbrand 200 1000 here, and in this case, now we're just going to get a random value each time. Now, if I had done this instead, this language side method, lowercase xbrand. Now, yes, it's true that this does generate random numbers if we just evaluate it by itself. But when we put a language side random number generator in a SynthDef, what happens is when we add the SynthDef, the interpreter says, okay, what do we have here? Xbrand, okay, 327. That's the number, and it bakes that number into the SynthDef. This evaluation happens immediately. Then the SynthDef gets compiled and built and sent to the server, and the frequency will always be that value, whatever value it happened to be, right? So if I, always the same. And we're saying, what gives? We made it random. Well, you made it random once, and then that random choice happened once and got burned into the algorithm. So that is why we use xbrand, which is a unit generator. And unit generators do not get evaluated language side. They stay a unit generator, and they go and join the rest of their unit generators on the server. And when we create a synth, that's when the UGen xbrand jumps into action and says, ooh, I got to make a number, and it makes a number. So every time we make a synth, we'll get a different random number. So that is my quick spiel on randomness in a SynthDef. It's always good to use these UGen versions instead of the language side versions. Let's revert back to our argument version. All right, and forgive me if I'm repeating myself here, but I think I haven't covered this yet, but should come as no surprise to you that specifying musical information as a value in hertz is clumsy if you want to do stuff like scales and semitones, because, start at, 466, and, we want to go up a semitone, what is that, 480 something? Okay, not quite. Very clumsy, right? So that's why we have things like number.midi cps. This takes a MIDI note number and gives you the value in frequency. Right, so 60, 61, C sharp, D, D sharp, does the math for you. Now, I do not recommend doing the math here, because that means every synth has to do that calculation, and we kind of add a little bit more work for the server. It's better to do it over here in the language when we create the synth. So do this, and we want the octave above middle C. Yeah. So that's convenient. Similarly, if we want to specify amplitude in decibels, we can do that by providing some digital decibel value. It's got to be 0 or below. 0 is the highest possible value, and we say dbamp. And that'll give us the corresponding normalized amplitude value. So this is nice if we say, let's start this at minus 12 decibels. And then we want to bring it down by 6 decibels. We just say, okay, well, minus 18. and down it goes. So just alternatives for expressing common musical information. You can go the other way too. ampdb takes an amplitude value and gives you the decibel value. And if you want to figure out what MIDI note number 400 hertz is, cpsmidi. And it's 67 1/3 of a semitone. All right, and then the last thing I wanted to point out is a few really nice, handy server tools. And I think we've seen some of these incidentally, but there is the server meters. So this will tell you the level of your signals going to your output channels, your speakers. I know we've seen plot, right? We'll just plot 50 milliseconds of a sine wave. So this is a great way to observe waveforms kind of out of time. You just want to see a few seconds of what something actually spits out without sending anything to your speakers. Plot is very handy. If you go to the plotter help file, there are a bunch of keyboard shortcuts that are active when a plot window is frontmost, which lets you kind of zoom and change the display mode, whether it's like points or lines or histogram. And you can even make it editable, like if you want to just like draw on it for some reason or something. So a lot of useful keyboard shortcuts there. We can poll a unit generator. Like if we have our envelope here, we can just say .poll, just to actually see what values come out of it as they are happening. And so what we had there is our envelope starting and ramping up to its peak value and then decaying to its sustain level, and then being released to 0. And you can change the frequency at which values are polled. I think the default is 10 per second. I generally would not recommend more than 30 or 40 or so. Remember, you can only refresh your screen, I think, 60 times per second. So you can't say, okay, give me 1,000 values per second. Something's going to break. But you can do up to 20 or 30 is okay, I think. Yeah, this will give you more values. Yeah, so it's a little bit more fine-grained. But just nice to be able to see the numbers as they're happening. That's poll. The scope. This is also creatable with s.scope. And if you've taken my 407 or 409 class, you've probably seen me use this a million billion times. Just a way of visualizing a waveform as it's happening. You can zoom horizontally, vertically. There is also the freak scope, which is a spectrum analyzer. It's a little bit limited in terms of what it can do. You can't really resize the window. You can't resize the window, period. It's not a sort of super fine appearance, but gives you something to work with. Right, we can bring this over here. Right. Sometimes convenient. Let's see, s.volume.gui just gives you a big volume meter for everything. You like a volume meter? Well, there you go. It's also available if you just click on these numbers down here. You can bring it up, bring it down. This globally affects everything coming out of the server, and you can always restore the volume to 0. You can also mute. I think I showed the node tree a couple minutes ago, s.plottree. This just shows you all of the processes that are on the server and all of the groups, all of the organizational structure. When you make the meters, that actually creates a pair of synths. Input and output to meters. If we close this, those go away. When we make a synth, there it is, and we can free it, and it goes away when the envelope finishes. So if you play a synth and you don't hear anything, it's good to check the node tree, because if you don't see anything on the node tree, it means your synth, probably you didn't add your SynthDef, or maybe there's some syntax error in your code. But if you do see a synth and still don't hear anything, there's a problem with your algorithm somewhere, like something's getting multiplied by 0, or who knows. Okay, and then here's a really nice one. S.make GUI. This brings up a little graphical window. The main reason I like this is because there is a record button. You can hit record, do whatever you like, and then when you're done making sound, you hit stop, and that went into my SuperCollider recordings directory. It'll print a path in the post window, and I'm going to see if I can track that down, actually. Let's do, yeah, there it is. This is probably one of the best tools for new users because you don't want to do all your logistical stuff in SuperCollider. You just want to use it as a sound generator. Right? Just make some cool sounds and then pipe them out, and you can just drop them into any audio editor or DAW and just work with them. So here's the sound. Right? I'll play this here. So it's real-time rendering to audio file. Very handy. And that's it for that section. We're going to move on, unless there are any questions on any of that. Okay. All right, so normally I start this class, the sort of creative part of it, with synthesis. And the more I think about it, the more I find that that's kind of a tough avenue to get started with, because you kind of have to know things about, like how do I actually do FM synthesis? What is wave shaping? And it requires a lot of, explanation to do kind of really subtle, interesting stuff. So I thought we'd start with sampling, because all or most of you probably have samples on your computer right now. You could, or download some from the internet or pull some from some repository somewhere. And samples, audio files, they can contain anything, right? You can sample whatever you want, just take a recording device, grab some sound. And it's really quite easy to just dump it into SuperCollider and start playing it fast and slow and upside down and backwards and with many copies and just making some cool stuff. So we're going to start by introducing a class called buffer. A buffer is it's a type of object which is not unique to SuperCollider. It's something that comes up in all different computer contexts. It's basically a block of memory that is allocated and in which you can store data. And in this case, we're going to store samples that make up an audio file. And the main way to do this is to read something into a buffer, which is buffer.read, and we're going to capture the result. And there are two things we need. One is the instance of the server on which this buffer will live, and that's pretty easy. We just want the local server S. Then we need a path, an absolute, file path to the file we want to read. And I have prepared a little folder of sound files. So here's my folder for the week, and I've saved my code file in this subfolder, and I also have a folder at the same level containing a bunch of stuff. This is a flower pot played with yarn mallets, flute, flutter tongue, key click, glass bottle. This is me talking about my brain exploding.
It just completely broke my brain. I had no idea what I was hearing or that sounds like this could exist.
Prayer bowl, PVC pipe, rattle, snare drum. Okay, so just a bunch of stuff. We're not going to use all of this, but I'm just a mishmash of, whatever. So, any of those strike your fancy? Which one should we read in? Flower pot. Excellent choice. Flower pot it is. So now this, trust me when I say the actual path to this file is like 12 layers deep, right? It's like folder within folder within folder within folder. So I don't want to type all that out. The easiest way, the way I prefer to bring, strings of file paths in here is to just drag and drop. You ready? Don't blink. There it goes. Just drag it right into the editor, and it becomes an absolute path string. Wonderful. And we're ready to run this. So we just put the cursor on this line and shift enter, and we have a buffer. And now just to confirm that it worked, you can say b.play and run it. There we go. And we can just command period to stop that. Right? This is just like you can't do very much in terms of interesting sound. This is just to confirm, yes, it's in SuperCollider, it's accessible, it's ready to go. We can plot a buffer, although I would not, if it's a big buffer, I wouldn't recommend resizing this window because it's actually a lot of data to plot. This buffer is 22 seconds long, so that times the sampling rate is the number of, I think, yeah, it's mono, I think. So it's not really going to render well, but this is just another way to say, okay, great, there it is, right? We've got our buffer in there. And while we're on the topic of duration, we can say b.query, and this will print a chunk of information relevant to this buffer. So every buffer has a bufnum. A bufnum is an integer identifier that's unique to each buffer. Sometimes we need to know the bufnum of a buffer, but usually we can just get by without it. But you know, this one is the first one we loaded, so it gets a 0. Next one's going to get a 1, etc. The buffer has 990,208 frames. Now, frames are like samples, but slightly different. So if we imagine like a stereo file here, right? So there's the left channel, there's the right channel, and you know, it's made up of samples, right? Individual values like this. Right? So this is a sample. Right? This is a sample. This is a channel. Right? This is a sample. This, see if I can do this. Is a frame. So number of samples equals number of channels times number of frames. Right? So if it's a one channel buffer, the number of frames equals the number of samples. It's just one sample per frame. But if we have a multi-channel buffer, like stereo, quad, whatever, then one frame is going to contain multiple samples. And we don't really need to reference individual samples, because when we want to start playback somewhere, we just say start at this frame. Right? And we just want to say this point along the timeline. So subtle difference. Yeah, we can see it's a one-channel buffer. So, and this is the sample rate at which it was recorded. You can deallocate a buffer by freeing it. So if we run this, it's gone. Cannot play a buffer that has been freed. And you can also say buffer.freeAll to just free all the buffers. If you have lots of buffers, you just want to wipe them all away. All right, so let's load this again. And let's make a simple SynthDef to play this buffer. Because we can't just rely on this. This doesn't really do anything interesting. It just plays it without any variation. So we're just preparing a few things here. Just getting our SynthDef ready. So this is kind of the meat and potatoes here. We got a signal and we want it to play this buffer. And the UGen that plays buffers, well, there's two of them, but I'm going to focus on one right now. It's called PlayBuf. And we'll go through these arguments one by one. First is the number of channels, and this has to match the number of channels in the buffer. And from querying it, we can see it has one channel. We can also say b.num channels, and that gives us one as well. And this number can't be modulated. So we can't say, making an argument or something like this. If we do that, we're going to see an error message. By design, every UGen and every SynthDef has to have a fixed channel size when the SynthDef is created. And it's not even really a very sensical thing to modulate the number of channels in a buffer. It doesn't make any sense because the sound file has some fixed number of channels. You can't say, okay, now, play your other what other channel? There's no other channel here, right? So you just have to put a number here which is consistent with the sound files that you're going to use this SynthDef to play. Next is the buff num of the buffer you want to play. Now, we can just put 0 here because we, checked and we know it's 0, but this is not a great idea. It's very much the same as saying signosc.ar 400. It's like, okay, that's always going to play 400 hertz. We might want to use this SynthDef to play one of many mono buffers. So the right thing to do is something like this. Or maybe even 0 here. 0 is fine. So we're making an argument so that we can specify a different buffer if we wanted to. Of course, we'd have to load that buffer first. Right now we just have the one sound file, but this is all fine and well and good. And that's enough to make sound. Just the number of channels and the buffer to play. Yeah, and here we say, okay, let's make a synth, and here's the buffer I want you to use, the one that I've stored in B. And immediately, you might notice the pitch is different. Here's the original. What is going on here? Because this one plays the right pitch, but suddenly this one plays a different pitch. Now, the reason this is happening is because this buffer was created and recorded at a sample rate of 44,100. And I am currently running the audio server at a sample rate of 48,000 samples per second. So here's, up here we have our sound, right? And it has 44,100 samples per second. And then here's my server, which is running at a slight, I'm going to draw this in an exaggerated way, right? But it's a faster sample rate, so there's more samples per second. And if we just play a buffer without trying to do any sort of management, then SuperCollider has, these samples to work with, and it's just going to map them 1-to-1, right? So basically everything gets kind of squished together, and the pitch changes, I think. I might have drawn this backwards here. No, I got it right. Right. That's the original one, but because we are playing a lower sample rate buffer at a higher sample rate on the server, the samples get a little squished together and the whole waveform gets, contracted. And just to prove to you that is what's happening, the third argument here is rate. So what we want to do here is compensate for the mismatched rates. And so the way to do that is to, well, a stupid way to do it is to just do the math here and just, scale the playback rate by this ratio. If we run this SynthDef and do this, now it's right. But this is not a good solution because if you bring this to somebody else's computer, maybe they're actually running the correct sample rate, and then you've shifted the playback rate for no reason. So there's a unit generator to handle this. Buff rate scale. And we'll just take this and pop that in here. Now what this UGen does is it says, okay, you want me to play this buffer, and I have the ability to check the server's sampling rate. I'll do the math for you. And it just divides the buffer's sampling rate by the server's sampling rate and scales the playback rate by that amount. If they're the same, the result is 1, and so there's no change. But if they're different, they get scaled by the appropriate ratio. So now we got the right pitch. But maybe we want to now actually musically manipulate the rate. So what we can do is add a rate argument. And this number here is a ratio. It's a speed ratio. So 2 means twice as fast, 1 octave up. 0.5 means twice as slow, 1 octave down. So if we do this, now we have the ability to say rate 2. Right? Just command period that. And like frequency in hertz, this is, dicey if we want to do semitones. It's good for harmonic series, right? Because you just, as I was just showing. But we can do MIDI ratio. So this is a semitone value. It can be positive or negative if you want to go up or down. Yeah. Yeah. And I'm hitting command period here because there's more to be done here. When we play this, we might not necessarily want to hear the whole thing, right? Because right now, it's just going to play to the end. And if we just play it with the normal playback rate, it's going to take 22 seconds and change to actually get to the end. And, I don't really feel like waiting around for that long. So let's keep going here. But we're in good shape because now we can change the playback speed and, by extension, the pitch we perceive. All right, you remember done actions, yeah? Done actions from envelopes. It's an integer which tells the synth what to do with itself when a finite UGen has reached the end. And so envelopes have an end, so does PlayBuf, because it's going to play a buffer. And it's going to get to the end at some point, and it needs to know what to do. So we can say done action 2. It's actually the last argument, but it's okay, we'll just skip ahead to it. And so now, I'll make this 2 octaves up, so it's going to take like 6.5 seconds to finish. There it goes. Done action 2 takes care of that. There is also an argument loop. And this should be 0 if you don't want PlayBuf to loop, and it should be 1 if you do want it to loop. And looping means if playback is moving along in this direction and it gets to the end, it checks its loop and it says, oh, it jumps to the beginning and keeps going. Same works with backwards. If it goes backwards and loop is 1, it's going to jump to the end and do it again. So we've set this to 1. And when loop is 1, the done action gets ignored. It does it again. So we're going to have to hit command period on that as well. All right, how are we doing? Okay, so let's address the whole 22-second business, right? What if we just wanted to play a little chunk, like a half-second chunk of this buffer? How do we do it?
SuperCollider coding, like would just be cut it out in Audacity.
Yeah.
Sample that.
Yeah, right. That's absolutely correct. If we want to do something which is essentially going into some waveform editor and saying only you, right? Only you get to play.
You apply an envelope onto the signal.
Exactly. You use an envelope to modulate the amplitude, and the envelope is what's going to get done action 2 instead of the PlayBuf. So let's just say, okay, we'll just make you loop. Not even going to bother with the done action. And we're going to make an envelope. And this envelope is going to control the amplitude, just like it did up here. In fact, let's just copy it, right? Copy that and that. And maybe we'll change it a little bit, but essentially, yeah, let's make an even simpler envelope, one that doesn't actually sustain. like something like this. So we got an envelope. It goes from 0 to 1 to 0, and we'll just briefly plot it so you can. Right, it's just a little percussive envelope, and it is right multiplied over here. Yeah, and it's awfully. Oh, you know why it's quiet? I think is because well, not entirely sure. Let's give it an amplitude argument. Yeah, so now, well, I think it's quiet because we're at the very beginning of the file, and we're just taking the first half a second, before the flower pot has really become fully, vibrational. We could do something marginally irresponsible here and boost the amplitude. Yeah. Right. But, no harm done. And, so what if we wanted to play from somewhere in the middle of a file? Well, PlayBuf has another argument called start pause, which is the frame on which we'd like to begin. So we'll just make an argument for ourselves. It's going to be 0, which means start at the beginning. But we can now, let's expand this a little bit. We can say, if we want to start 1 second into the file, we can't say 1 because start position is a value in frames. And there's, in this case, I don't know if it's 44,100 or 48,000 because they're mismatched, but I don't know. I'm not actually sure. But I'm going to guess it's this. Right? So now it's going to start at frame 48,000. It might actually be this. And we can say 2 seconds. Okay, this file is not a great example because it's kind of one thing the whole way through. But if you listen very carefully, you'll hear that the sound is a little bit different. Yeah, see we're at the very end here. There's 22 seconds. This is a lot more interesting if we were dealing with it just completely broke my brain sound file, because that's me talking and it's going to be something noticeably different no matter where we start in the file. All right.
Does that mean then whenever you loop, it'll go back to the start position?
So if loop is 1, PlayBuf has this internal pointer, which is moving at a speed determined by rate. And if loop is 1 and it gets to either the last, or if it's going the other way and goes to the first, it's just going to pretend that the sample at the other side is right next to it. And it's just imagine taking the ends of the buffer and joining them together into a circle. Right? So yes, actually, we could modify this to show you exactly how that works. So let's make this envelope 3 seconds long. And we're now going to start at the 22nd second. And so you should hear it fade out and then immediately start back at the beginning. Did you hear that? Yeah, so we start at the end. The envelope is about 3 seconds long, so we begin, it starts its decay, but we manage to get to the end, and loop says, we're going back to the beginning, and so it will wrap around like that. If you don't want that to happen, then you need to be more careful with your start positions, right? Because if loop were 0, then we would play this, and it sort of gets to the end, and PlayBuf says, whoops, I'm done, right? I'm not supposed to loop, so I'm going to stay here. But the envelope is still decaying, so you'll get, depending on how you're waveform has been edited, and like if it has like an abrupt stop at the end, or if you've put an artificial fade out there in the waveform itself. You just have to be cognizant of what is actually in your buffer. All right, well, unfortunately, we're out of time. There's more interesting stuff we can do with buffers, primarily involving the final argument, which we haven't dealt with, which is trigger. Anytime PlayBuf receives a trigger at this input, it will jump to its start position. So we can take an impulse generator and repeatedly cause it to jump back, and so we can kind of stutter and loop small sections of a buffer. And we can also link that trigger with the gate of an envelope, so that every time it gets a trigger, the envelope resets and the buffer also jumps, the PlayBuf also jumps to its start position. And we can get really cool rhythmic textures. And then let's not forget that we are just creating one synth. And there's a really powerful combination that is a result of creating synths with iteration. You say 20.do, boom, like a synth, and give each one an algorithmically or procedurally generated start position or playback rate. You can make chords, you can make clouds and textures and things like that. So that is where we will start next week. And I have a whole bunch of additional topics: filters, granulators, sequencing. So we will make our way towards really cool and interesting sound, which hopefully will start to feel more and more at your fingertips. So I'll write a homework assignment, and I think it's going to be another 2-week deadline, probably, just to give us all a chance to digest and get through some more buffer stuff. All right? Very good. See you next week.